be that late. Okay. Oh, yeah, call drill and stuff. Okay, let's just go over where we are and what we've still got to do. We finished 19 last time, and we'll be doing Chapter 19 lab the last 2 hours of today. I don't think it'll take you 2 hours. It's sort of a fun lab. Most students tend to enjoy this one. I did give you last time we took the Chapter 18 test at the end of the time. And I gave you Chapter 19 test, which was a take-home test. So be sure you get that before you go today. And so we'll get that covered. So today we'll start Chapter 20 and go until about 3:45, and then we'll stop there and do the, if we haven't finished Chapter 20 by then, we'll stop there and do the lab for Chapter 19, though it doesn't have that much to do with Chapter 19. It's just the lab that covers this kind of stuff, you know. And then the odds are we'll finish 20 then on Tuesday and have the lab for 20 on Tuesday. Probably start Chapter 20, where we don't do 21. We jump to 23, I think it is. And this class is actually going along really at a good pace. Geologic time, we've never had time to do that one. And then the next one, Chapter 22, is the atmosphere. And usually we're running out of term and don't have time for that to get the weather and oceanography in. So I usually skip 20 and 21. Yeah, we're going to get there at the end. So we'll be starting Chapter 20 today. I thought I turned on the projector, but nothing is happening. Sometimes it doesn't connect. Okay. Any questions on anything we've done so far? All right. Let's see, we've done 1, 2, 3. Second?
The questions that were supposed to be turned in?
Yeah.
On Chapter 18, right?
Yeah.
Those were just the lines, there were 50 of them questions, right?
15 or more, right. Yeah. Okay. And now a few people turned in the lab part with no questions, and I think I actually got somebody that turned in the questions with no lab part. So I'm not sure they're here now, but I'll have to check on that. In fact, maybe that's a good thing to go over now. I am still waiting for I'm still waiting for all but one person to turn in a paper, because that's all I've received so far in this class, is one. Okay, Lab 1, I've only got one person that hasn't turned in Lab 1, and he's not here right now, so I can't do anything. Everybody did Test 1, I've returned those to you. Lab 2, I've got 1, 2, 3, 4 people haven't turned in Lab 2. Test 2, 1, 2 people haven't done Test 2. Lab 3 was the moon lab, and only one person's turned that in so far. Test 3, everybody's done. I'll return those to you. If you didn't get them, see me while you're doing lab today. And I'll even mark Fred here. Okay. All right, just going over what. So lab test 3, everybody's done, and I've returned to you. Okay, lab 4 will be the trip to the planetarium, just to keep things going. That's going to be the first Tuesday in October. The 3rd of October, I believe it is. Does anyone else know what day that is? 3rd of October. Yeah. Say again?
No, that's a Thursday.
What's that? Okay. First Tuesday in October. Kind of an important day. Not have anything to do with the class. Your civic responsibilities. Any of you live in Birmingham? Oh, yes. That's when the runoff for the mayor and some of the city council and Board of Education seats for the City of Birmingham elections. That runoff election is that Tuesday, so don't forget to vote in that if you're from Birmingham. Okay, so that'll be Lab 4. Lab 5 was the properties of minerals and stuff like that. That's 1, 2, 3 people haven't turned that in. Test 4 on that same chapter was 1, 2, 3, 4 people haven't done test 4. Now, one of you did you do that today or no? That was earlier. Yeah, okay. That's, all right. Lab 6, which is the one that has the questions with it.
Last question.
Ah, fantastic.
Can I just
Thank
type
you.
those?
Yeah. Okay.
Yes, I just
All right. Good deal. Thanks.
It's so much faster, so much easier.
All right.
All
right. Okay.
I remember in the 80s when you actually had to learn how to type without looking at your hands. They don't make you do that anymore, so I can do it pretty fast.
All right. Okay, now let me correct some of this stuff. A few people have turned in some stuff I haven't finished grading, so that may be, and then I've just got a whole bunch more, so, but let me continue. The Lab 6 was the one with questions, so I got a few more of those in now. Test 5, I'm still grading on those, and a few people haven't done that, and then today we'll do Lab 7, and some people have already turned in Test 6, so, and that's the take-home test. So that brings us up to date. Let's get started. Are there any questions before we get started on Chapter 20? Chapter 20, Chapter 19, remember, was building the Earth's surface. We did that by folding, faulting, volcanic activities, earthquakes, that kind of stuff. In this chapter, we start talking about how that surface gets shaped. In other words, worn down. So we were building it last chapter, wearing it down this chapter. Okay? And this is a picture. Anyone recognize what you think that might be?
Grand Canyon?
I imagine it is. They don't have a caption on it to say, but I wouldn't be surprised. It may be one of the other places that has these really remarkable. One thing that leads me to think it is, most of Grand Canyon is fairly horizontal layering, so it's mostly sedimentary rock, which means that's probably why it eroded so easily, because sedimentary rock usually is as hard as igneous or metamorphic. So again?
Like sandstone.
Sandstone, yeah, and that kind of stuff. And then the other feature of it is, of course, the very intense weather. What has made that real deep canyon there? What is the reason Grand Canyon's there? Huh?
Erosion.
Okay, erosion certainly, and what made the erosion? Yeah, what water runs through the Grand Canyon?
Rio Grande. I don't know. That's just a guess.
Colorado River. Colorado River. Okay. Okay. Colorado River, and boy, it runs through there too. Okay. And that's what's continually eating away at the Grand Canyon. And that's what we're going to be talking about this chapter. The core concept here is the surface of the earth is involved with an ongoing process. We've seen that
Do they
before.
think that the Grand Canyon is just going to be a bit empty hole someday?
I don't know. It's just going to keep wearing down. In fact, the Grand Canyon is really interesting to archaeologists because they can literally measure centuries, if not millennia, of strata there. So they probably hope it will just keep wearing down. I guess it will. So the surface of the earth is involved in an ongoing process. Hasn't just about everything we talked about been an ongoing process of destruction and tearing down of the higher elevations. Here's a picture. Anyone know what that's a picture of?
Not Niagara Falls.
No, it's not Niagara Falls. It is a waterfall. This is rock over here, or stone. What sort of color is that?
Sand colored. Yellow.
Yellowstone, yeah. That's
Ooh,
all right. That was a hint. Okay.
Right in the green area.
All right.
I'm gonna let you believe it.
This, I think, is the upper falls of the Yellowstone River that feeds into Yellowstone Lake. There are two of these really mighty waterfalls there. And as you can tell, this is a very steep V-shaped valley. The water has been eating away. And boy, that water flows too. And that's the Yellowstone, I think it's the upper falls of Yellowstone. We were in Yellowstone for a day this summer, between summer and fall terms. And it was so crowded we couldn't get close enough to really see either falls well, but we had seen them both before, so we tried to go somewhere else which wasn't so crowded. Just about everything was, but it's a beautiful, beautiful sight. And way down there is where the river is running. But there's waterfalls there, and then there's another one, and then it empties into the lake.
Did you see it about it down there?
What's that?
Did you see it about what did we end up barrels? Did you see it about it down there?
Okay. We were close enough at Yellowstone this time. The last time we were there were people down there. The one we saw was on the Snake River, and I mean, that is really far down there too, and the people looked like ants. They were that small because they were that deep. It was really incredible. They were down there in canoes and kayaks and that kind of thing. This is I don't know. I'm trying to remember now if we did see anyone down there. It seems like we did, but that's a pretty hazardous place to be between the two waterfalls because there's not a lot of easy ways to get in and out. And if you go too far down, you go over the next falls, and you don't want to do that. So I'm not even sure they let people down there. It seems like one of the times we were there we saw it, but that may have been further down after the second falls. But in between the two, I wouldn't be at all surprised if they don't prevent people from going down there. Okay, so how is the Earth's surface shaped? Okay, one of these processes is called weathering, and there's a pretty good reason for that. Most of the elements of the weather contribute to that. What would be the definition of weathering? Here's one: slow changes resulting in the breakup, crumbling, and other destruction of solid rock. Okay? Go back here. At one time, this valley was not much of a valley. It was up to here. And Nick came in then. Okay. I know you're in here. I will find you. There you are. Okay. And this Yellowstone River has eaten away and eaten away and eaten away, just like Grand Canyon, the Colorado River has done that. So that rock used to be, in fact, this waterfall used to be somewhere over here, out this way. But it's eaten down, so it's falling, and so it's eaten more down there. So it's a slow, steady progression of, I've already got Hunter here, of the thing. So it's a slow changes resulting in the breakup, crumbling, and other destruction of solid rock. Okay? They love threes, don't they? Three major processes: physical weathering, chemical weathering, biological weathering. They spend a lot of time on physical and chemical, not very much on biological. I'll throw in a little bit on that. Okay? So, these processes contribute to the rock cycle. Now, how do you reckon that's true? Say again? Exactly. You have to break up those igneous rocks and metamorphic rock, and even other sedimentary rock to get the sediments they're going to make into sedimentary rock. So sure, that's all part of the cycle. Okay? That's not the best part of it, though. Without these processes, we have no soils. With no soils, there's no food. With no food, we're not here, okay? Couldn't be here. So it's not all a bad thing for the rocks to be broken up. That's how we get our soil, okay? It also contributes to the movement of rock materials over the Earth's surface. Sometimes that's less good than others. Other times it might not be so bad. Now, one of the ultimate processes that does a lot of this is erosion. Basically, all these things sort of contribute to the process of physically removing weathered materials. Physically removing weathered materials. Now, that may not be such a bad thing if it's at a place that those materials are not all that useful, but if those are the soils on which we are trying to grow our crops and they get removed, that's not a good thing, because then we've lost the source of the soils. They've gone into the bottom of a lake, down into the Gulf, somewhere that are not very useful. So generally, erosion is not a good process, okay? The breakdown, some of these processes are pretty good in that they form the soils, but if we lose the soil due to erosion, not so good. Okay, as you can tell, I'm from an agricultural background. Yes?
I was going to say, could you not changing it?
Oh, yeah, sure. Because I grew up on a farm, and we tried to, best we could, not to have fields eroding away. Did practices to keep that from happening or minimize it. Then my graduate work was in agriculture, so erosion is not a very pretty word with me. Okay. Any questions on this? We're going to, for the next few slides, talk about these various kinds of processes. First physical, then chemical. Like I said, they don't even give you a slide on biological, but I'll include that. Now, a little bit of a lead into that, the very next, I think the next slide will not say physical weathering at all. It will say mechanical weathering. Those two mean the same thing. Physical weathering, mechanical weathering. They mean the same thing, so you can refer to either one of them. Okay? So what is mechanical weathering? The physical breakup of rocks without chemical change. Because if it's chemical change, then it's chemical weathering. Okay? So if it's a physical breakup without chemical change, that's mechanical or physical weathering. There are a couple of these processes. They call them disintegration processes. One is wedging. That's not what you do to your little brother. Hey, okay? He has a little brother. Okay. So, what this is, and here's a decent little, maybe not the greatest of illustrations of that. They say by frost or by trees. Okay? We're going to go into that a little bit both ways. Let's first say, I don't like the term frost. That doesn't seem strong enough. I say ice or trees. What happens is you have a rock. Okay? Now that rock has a little crack in it. Now where did that come from? Maybe it broke sometime, maybe something hit it and it cracked a little bit. Or maybe it had some chemical weathering. For some reason it had a little crack, and guess what? If that rock is exposed, water is going to find its way into the crack. Now if it's a cold climate, that later that water freezes, what is one of the unusual aspects of water? It expands when it freezes. Not many other materials on the planet expand when they go from a liquid state to a phase to a solid phase. Water is about the only one. What happens when that happens? As it expands, it was filling the crack completely. It expands, it forces the crack to be bigger. Then the next season, more water gets in, it expands again, pushes further. At some point, the rock breaks off. Okay? Yeah, falling into the ocean, yeah. Science fiction. Okay. So, But, in reality, all coasts are eroding into the ocean. They're not falling into the ocean, but they're eroding. And they do have mudslides sometimes and stuff where great quantities could go in. Okay, but it's not a breaking of the earth. Okay. So that's the wedging process by frost. Now, here's another, you'll see something like this in a little bit later too. Massive granite was originally deeply buried and under pressure. And then erosion has happened and worn it away, and that piece of granite got onto the surface. Well, there's not as much pressure on the surface. As erosion exposes more of the granite, it is, they say, unloaded. In other words, the pressure is reduced and uncompressed, and it may break apart in sheets. Now, that's called exfoliation, which doesn't, here it is. Okay. Exfoliation is, I thought it was on another slide. They haven't done the tree. That's on the next slide. In fact, I think it will still show. So let's.
When it says by trees,
No.
does that mean like by roots?
Yes, exactly.
Break them open and
Yeah.
stuff?
So while we got this slide here, let's just jump on to exfoliation.
Okay.
And that is reduced pressure, like we were describing here, effect. The fractures caused by the expansion of the underlying rock, which has greater pressure, less on top, it forms cracks. The cracks then allow, wedging or other things to happen, and you tend to fall off. If you've ever been to Stone Mountain, Georgia, surrounding Stone Mountain, Georgia, there's gravel all around there because that's exfoliated from the rock that was on the surface. That's weathered and fallen down. Look at most of the road cuts. A lot of times you'll see signs, caution falling rocks, because there's always this weathering going on, and you'll have pieces, chunks falling down. Okay? So that's wedging by frost, which interacts with exfoliation as well. Exfoliation is more the reduced pressure as it comes to the surface, forming cracks, and then the weathering process is chemical, physical, biological, all those, then break it into smaller pieces. Now, as you said, the trees. Where is most of the activity in a tree root? Do you know?
The trunk?
Second?
The trunk? Or the
Okay, yeah, below that, in the root. Where is your activity going on?
At the tip of them?
Very much so. They actually call that root hairs. You can hardly see the things. They're so fine. The roots send out these root hairs because you see a big old root, that's hard for it to absorb water, minerals, nutrient, or anything else. So it's the root hairs where all the activity, because they're very thin, lots of surface area, very thin cell walls and things, so the nutrients and water can move freely through them. So these root hairs are out there, and they're mining the soil, basically. They get out there and touch that. Now, how can a little bitty, tiny root hair mine nutrients and get water out of the soil? How it gets the nutrients, the tree secretes an acid. Okay? Biological weathering, chemical weathering, both of those are going on together. They secrete an acid, and the acid breaks down the stuff right around it, and then the root hairs suck it up. Well, they're doing this all the time. That's how they get the moisture and stuff, and they grow. Well, they're down in this little fissure, this little crack, just like the water is, and they get their nutrients and stuff, and they grow, and they split the rock, break it down into smaller pieces, and that's what this is showing. Here, this is not a rock. This is a piece of sidewalk, and that root grew under there, continued to grow, pushed it up. And mine too. Okay. A big old white oak right there. Okay. I've seen this up at Smith Lake. It's just unbelievable that roots got down into what were cracks, expanded, and they lost the top part, and they're still sending out their root hairs into other parts of the rock, and ultimately they'll break apart. Odds are the tree will fall down because the rocks have fallen around it, but it's just amazing sometimes to see those trees up there with, that's the only thing holding them up. And that started with a little bitty root hair going down into a crevice and wedged the rock continuously. Amazing how much power those little roots have when they're growing. Okay, that's wedging. And those are examples of mechanical weathering, also physical weathering with no chemical. I mean, they can interact with the chemical change, but to be physical weathering, the chemical change is not part of the picture. Okay. Now we move to chemical weathering. Okay? This is decomposition of the minerals by chemical reactions, not just physical reactions. Now we'll come back to some other physical changes, physical weathering, a little later when we're talking about the big pictures. But right now we'll deal with this. So decomposition by chemical reactions. Again, they love threes, okay? 3 major chemical reactions they'll talk about. The first of these is oxidation. That almost is what it sounds like, reactions with oxygen. Where does it find oxygen? The air is just about 20% oxygen. So it's all around. And oxygen is a very reactive element. It likes to combine with just about anything it can get its bonds onto, okay? Reactions with oxide. One form of oxidation, the red iron oxides. Where have we seen those? Rust. That's exactly. You expose a piece of metal, if it's got any iron in it, steel, anything like that, expose that to the air and moisture, in time, it's going to rust. There's no way around it, except when Willie comes in. Okay. All right, good deal. Okay. We're in chapter 20. We're somewhere around page 508, 509, somewhere in that range. Okay? And by the way, before I turn the pages there, on the bottom of 506, it's a tremendous shot, nice photography there. You know what? I mean, it's a Utah's Rainbow Bridge National Monument is an example of a landform created by the sculpting power of moving water. Water did that. That was a lot of water, but the other thing, page 506, bottom of the page. For those, yes.
So, I want to show you something.
Okay, what's that?
Well, I just want to read it. Just
Share with class.
Yeah. Huh. Interesting. Yeah. Yeah. This is what is this in?
That is.
Chariots of the Gods. Boy, I read this many years ago.
I didn't know. That before you was.
Yeah, it was copyrighted in 1968. It was probably when I was in college. I don't remember the picture of it. An ancient iron pillar that does not rust. Okay? I do not know it. It cannot be accurately dated, but it is hundreds of years old and does not rust. Obviously formed by man.
Yep.
Okay? It wasn't naturally occurring. There are iron things today that don't rust, but that's because we have, what kind of steel doesn't rust? Stainless steel.
Go, Sam.
Now that doesn't look like that stainless steel, and if it's that old, that, yes.
What about the Leaning Tower of Pisa?
Mm-hmm.
What's the physical thing?
Okay, the soil is eroding away underneath it. It probably was built on rock on one part, but maybe limestone on the other part. The limestone has eroded, chemically eroded, which we're going to talk about, and the other rock, the granite, did not, or something like that. I don't know for sure, but I do know what they've done is gone in there and jacked it up because it was getting so, it was leaning so much, it was in danger of collapse. So they did jack it up a little bit and put reinforced concrete and stuff underneath. Because otherwise I think it would have already crashed by now. But, so oxidation, oxygen, a very yes.
Get back to the rainbow tree.
Oh yeah. Okay, that's where we were. Yeah, for those who didn't have the books here, there it is, and that was eroded by water. What this is telling you, this was harder rock here than the rock that used to be in there. But water ate its way through. How it got started, not too sure, but it continued to eat its way through. Now, looks like Utah is not a very wet state, so at some time in its past it must have been a lot wetter for that much water to go through. However, that does look like a waterfall in the background here. I can't say for sure that's what it is, but it sure looks like that. So there is moving water there. You can see there's a little water in the riverbed there, but you see all this gravel here is the residue of erosion.
So why do they consider it as being sacred?
Oh, you mean the Indians?
Yeah.
Okay, they didn't say anything here about it, but the Indians, American Indians, and many other cultures, they really, I don't know, this is not my area, but this is what I've read about. They basically almost considered creation itself their mother, their father, that the thing that like Mother Earth, you hear lots of people talk about that, they see that as part of the thing. So something that's this unusual, this spectacular, that they must think that must be pretty special to be like that. Oh yeah, there we go. Okay. Yeah. That reminds me of Charles Barkley's saying, Father Time is undefeated, when he's talking about athletes. Yeah. There's no athlete ever beats Father Time. Okay, I forgot to mark. Yeah, I'm trying to find you. There you are, Kelsey. Has anyone else come in since I called roll? I got Willie. Okay. Yeah. Okay. So, that was that figure before we leave the pages. Here on this one, for those who don't have the book, on page 507, the piles of rocks and rock fragments are abundant mass of solid rocks, evidence that the solid rock is slowly crumbling away. That is the harder part. The other part has been, that was one big chunk with not many fragments. Now it's lots of fragments with not very much big chunk anymore. Just shows that. And it may have taken thousands or hundreds of years for this to have happened, but it does happen continually. Okay? I really don't know why. It's a great picture of the little girl walking between the trees, but I guess what they're saying is you can see some cracks in the pavement. Not many, but you can see some, and that's because the roots are pushing it up. Okay? And so that's about where we are. 508, 509 type phrase. So, oxidation, anything that combines with oxygen, that process is oxidation. Now, where else do we see, you said rust, where else do we see red iron oxides? What is Georgia really famous for?
Clay.
Red clay. Georgia red clay. But Alabama has plenty of red clay too. That's iron oxide. Okay. There's not a lot of it. It's just coating the surface of the clays. Remember, the clays are submicroscopic particles, really tiny particles, and then the iron oxides are just a little film on the surface of them. So you're not talking about what? Say again?
Of each tiny little
Yeah, well,
It's
yeah,
covered.
the mass of it, yeah. And the thing is, it doesn't take much. Now, I can't remember if I told you this or not. The house that my parents built when I was in the 7th grade, when we moved down to the farm, we had lived in, when my father and his brother, my uncle, bought the farm and a place to live. They bought it from the same person, but they were separated. The land was down in Burke County and the house was in Richmond County, 7 miles away. So my dad commuted to the farm every day. And when finally they saved up enough money and stuff like this, then they built on the farm and sold the house in Hassel. Okay? The hill, the field right next to where the house was, red clay hill. I mean, just obviously a red clay hill. But the lower part of that field, away from the house, it was a low area, and it was gray. It was a swampy area, and it was gray. And growing up, I always thought, I think I told you this one. I thought the sand and the topsoil had all eroded off the hillside and filled in the low part, and that was the dark colored soil there that used to be on the top there. Found out, no, it wasn't. That was the same clay, the gray clay down here that you had up on the hillside. It was just a different color. Why? Because up on the hillside it was highly oxidized iron, and down here it was low oxidized iron. Still oxidized iron, but it was gray. And didn't we go into your blood? Did we talk about that? The red blood is oxidized and the blue blood is less oxidized. That's the same thing that happens in the clays. Really well aerated red oxide or iron oxides are going to be red. If they're less well aerated, they're going to be first go to a yellowish and then go to a grayish and actually can get quite dark. So, but iron isn't the only thing that oxidizes. Just about everything does. We're later going to introduce a term called humus. Anyone know what that is?
Yes.
The gardeners?
What did you say?
What's that?
I didn't hear you.
Humus.
Pronouns.
It's not humorous, but humus. Okay.
Yes.
Okay. Yeah, hummus is what you eat. We don't. He didn't eat. He's got food on his mind. Okay. Yeah. But that is decomposed plant material usually. It can be animal material too, mostly plant. And that's what gives the soil the dark, rich color. We'll talk about that later. That oxidizes. I mean, especially here in the South, I used to shred the leaves. We have 2 huge white oak trees, big leaves, and they would fall in the autumn. And we tried breaking them. Impossible to do that. So we bought what we call they called the chipper shredder vac. That actually chipped it up and made it into nice, stuff. And then we put it in our flower beds. So we didn't put it on the street anymore. We kept it in the yard. But like 10 times, it reduced the volume from like 11 bags to 1 bag. So it's much more efficient. But we put that in the yard, and within a few months of spring, all that is already oxidized away. Yeah.
I had an old shed. I have a pool. I had a pool, and there was a open bucket of shop. The chemicals.
Right.
Inside my shed, I had old saw blades, giant magnets, everything like from the 60s and 70s that just hung in there. I guess water got into the chemical bucket with the chemicals. I didn't go into the shed for a while, and when I went in, every bit of that metal was rusted.
Yeah.
No water touched any of the metal, but everything had a thick coat. Why did that happen?
Okay.
Horseshoes, everything that was metal that was exposed to the air.
Well, yeah, because in that closed environment, probably the humidity was quite high. So there was plenty of moisture in the air. Okay?
Yeah.
Water vapor.
Okay.
And probably the chemicals in the chemical reaction that did could have produced some hydrochloric acid, sulfuric acid, or even weaker, carbonic acid, some sort of acid that also was in the air, and that moisture and that combining with the iron just rusted away like crazy. Yeah.
So the worst rusting I've ever seen.
Yeah.
And quickly.
Yeah.
It's weird.
Yeah. It's a little bit of chemical, especially, and it could have either been an acid or an alkali, either one. Both of those. An acid is corrosive, and a base is caustic. But both of those will contribute to disintegration. So it could have been either one.
Thanks.
Okay. So that's oxidation. Anything combining with oxygen. And generally, what you were describing and what we talked about before, if something rusts, oxidizes, it weakens that material. I bet you those tools were not very useful anymore. Saw blades, not very, probably almost destroyed. Nails into the deck or something like that, if the nail rusts, you almost bet it's not going to hold the board as well because it, So oxidation is a deteriorating type thing. There's another, carbonation. Now, if oxidation is combining with oxygen, what do you think carbonation would be? With carbon. And it sort of is. Only it's not just carbon, it's carbonic acid. And what is carbonic acid? Carbon dioxide dissolved in water. Let me do a little bit of chemistry here. You don't have to know a lot of chemistry. Okay? What's that? Okay. If you have CO2, that's carbon dioxide, combine that with H2O, which is water. If they combine chemically, you have H2CO3. Okay? That's carbonic acid. So its reaction is carbon dioxide dissolved in water. Have any of you ever drunk any carbonic acid?
Yeah, probably. You don't know that.
I would say almost definitely. Have any of you ever had a soda? Oh! Now, some of the sodas, like the darker ones, typically are phosphoric acid. Okay, Coke being one. But your clearer ones, like Sprites and things like that, are usually carbonic acid. But even the Cokes have some carbonic acid because you have carbonation, which is carbon dioxide in water, carbonic acid. Okay?
Wait.
Not too good on the teeth. You drink too many of those for too long a time.
Coke eat up battery acid, man.
Well, it's not quite as bad as battery acid. Don't be drinking that either. Yeah. Battery acid is sulfuric acid. This is a much milder, weaker acid, but it's still an acid.
You drink sodas?
As little as I can get by with. When I'm driving, I've got to have a little caffeine. So I usually, if I'm driving long distance, or when I'm grading labs, I have to. I need something to keep the eyelids open. So I usually have a soda in the fridge, but sometimes it might last all week, or longer. So carbonic acid reaction, carbonation, and actually, the book calls it carbonation. I think it's much broader than that. I call this acidification. Any acid is going to do all these things. Dissolving limestone, wearing away teeth, breaking down materials, contributing to the rusting process, all that. Any acid. So I don't want to call it just carbonation, I call it acidification. Every time you see lightning strike or hear it, you know that some of the nitrogen in the air was oxidized to form a nitrous oxide. You combine that with water and you have nitric acid, which is a really strong acid. Okay? Anytime you have fumes going into the air, like you're burning stuff, you have sulfur dioxide, carbon dioxide. Any of those mixed with water, you get sulfuric acid or carbonic acid, nitric acid. It just shows up all over the place. So I wouldn't limit this to carbonation, but I'd say acidification. Okay. Now, they mentioned limestone, that arch there. My guess it was limestone through here. The water eroded it physically, but it probably also ate it away chemically by carbonation. And most of your places where you see it eating out like that. So, by the way, let's go back to oxidation. I mentioned that water is involved not directly in the chemical reaction, but water acts like the catalyst that makes it happen. If you keep something very dry, it's not going to rust as badly as if it's exposed to moisture, like Cece was talking about. And the reason for that, the water has nothing directly to do with the oxidation, but it is the catalyst that makes it happen. It's kind of like in your body, you have enzymes. The enzymes help digest your food or help do other bodily function, but they're not really part of the function itself. They just make the environment where it happens more.
That's kind of like silver water.
What's that?
Silver water, silver water,
Yeah.
even though they keep it inside the steel time.
Right. What you're trying to do is keep it exposed from being exposed to the oxygen in the air, and also the acidic part. Because what that is, silver, if it's silver or even silver plate, combines with the chemicals in the air, the tarnish is either silver oxide or silver sulfate or something like that. So yeah, you're trying to keep it from it. So some of them, they wrap them into cloths that have, retardant to try to keep that from happening. But come Thanksgiving, Mama's going to be polishing that silver. Yeah. Actually, the polishing the silver is just actually itself is eroding away the outer layer, so you get down to the silver again.
Are you actually polishing?
One type of process, we mentioned stainless steel doesn't rust, or at least doesn't rust much. That's an alloy with chromium, and maybe some nickel, something else to keep the iron from interacting with the oxygen. Another thing they do that's much cheaper than stainless steel, and by the way, stainless steel is also fairly brittle and expensive, so they don't do that. What else do they use? What kind of nails or process do you use? Galvanized. You know what galvanized is? Coated with zinc, exactly. Coated with zinc. And see, the zinc doesn't, actually the zinc does oxidize, but that oxidation of the zinc forms a protective layer around the steel that keeps the oxygen from getting to the steel. Okay? And that's that. Now, this is another really big aside here. Any of you have pecan trees? Okay. Have you ever had the pecans so they get that little dark thing in the meat that tastes really bitter?
Yes.
Okay? That, not always, but usually that's a form of zinc deficiency. Pecans need a lot of zinc. Zinc's not a very common mineral, so if the tree leaches it all out, you get that. Yes?
Isn't there a special drink out there that has zinc in it? I thought
Is there what?
Isn't there some sort of energy drink out there that has zinc? I think I've seen it like on commercials
Yeah.
or something.
It was thought a few years ago, I think it probably is true, that zinc helps you either not catch colds or get over colds more quickly. It does something, again, it's probably acting like a catalyst in your body to help, the cold from spreading. So I think that's what it is. Yeah.
Is there a zinc in orange juice? Because it seems like
Well, they can color it any way they want to. But it is very low amounts of zinc. But those tablets or lozenges is what I'm thinking of. The lozenges that have the zinc in them, they do taste metallic. Okay, very metallic. Okay. Let me find you. Trey, right? Okay. So yeah, zinc is usually thought of as being something good to take, either if you've been exposed to a cold or if you're catching a cold. Our pastor's wife, I mean, she's a huge proponent of zinc. Oh yeah, take that zinc. You know, it just tastes so bad. I don't like taking zinc, so I try not to get colds. Okay. All right. But anyway, carbonation or any acid, acidification easily dissolves the limestone. Okay? And guess what? Most of what underlies Alabama is limestone. And Tierra's here. All right. Anyone else come in? Sort of like a swinging door here. Okay. So, carbonation or acidification. Anything that eats away at stuff. And limestone's the major soil material, rock material that is very easily affected by acid. Okay? In fact, you can tell, that's one of the tests. If you had a rock, you can't tell what it is. If you take some vinegar and drop on it, if it fizzes up, the odds are that's limestone. Because vinegar is acetic acid. Okay? And the acetic acid will then release the carbon from the calcium carbonate, and you form that. Okay? So, water is somewhat involved with oxidation. It acts like a catalyst oftentimes. It's certainly involved with carbonation because the carbon or any other thing is dissolved in water. And hydration. What is hydration? Combined with water. Reactions with water. Second. Water is a very active chemical itself. Okay? It's not, if it has extra hydrogen ions, it's acidic. If it doesn't have many, it's basic. And both of those can react with things. But water itself has those hydrogen bonds. Remember when we did the lab and we were filling the beaker? And I said, keep putting more water, keep putting more water. And you could see it sitting on top of it. It should have been overflowing. And that's because those hydrogen bonds hold those water molecules against each other, to each other really strongly. If you've ever jumped into a swimming pool but landed on the belly flop, you know that hydrogen bonding is pretty strong. Well, that hurts like crazy. Okay. Some of us have more belly to flop than others, but never mind that. Okay. But that's reaction with water. Includes dissolving in water and combining with water. Now remember when we were talking about those sedimentary rocks, lithification, what were the two processes? Oh yeah, so long ago. Weeks. Okay.
Just they layer the sediment layers and it becomes. What do you ask?
What was the lithification processes? Two processes. Both were C's. Compaction and cementation. Exactly. And remember part of the compaction work? The compaction was you're squeezing out the pore space. And sometimes that's squeezing out the water. But what's left behind was the cementing agent. And that's what held them together. But then you go and expose that to water, the water starts dissolving that cementing agent now, and now the sedimentary rock starts falling apart. And you really see that happen. Reactions with water, that includes dissolving in water, but also combining with water. Now I mentioned earlier, especially in California, the mudslides. And I think I mentioned this before when we were talking about the clays. Some clays, in fact all clays, hydrate pretty easily. And that means they swell. We talked about the clayey soils, you'll see the cracks in the surface when they dry out because now they shrunk. They wet and they close back up. Well, that's combining with water, and when the clays get lots of layers of water in them, now they're slicker than whale snot, and they go sliding down the hillside. And that's why you get the mudslides there. No. Okay. I wondered who was listening. Okay. That's the old naval term. Okay. All right. There's actually a place, I guess it's Irondale. Do you know where Eastwood Festival Center where the Home Depot is? And
Yes.
okay. And that hillside there, right above that, there were, right on off Crestwood, yeah. There was a real rainy season. I think it was before we moved to Birmingham, and literally those apartments built up there, they started sliding down the hill. I mean, we were having sort of a mudslide, and they brought in engineering companies, and they tried all sorts of. If you look carefully there, you'll see holes drilled in the thing. You'll see reinforced concrete. You'll see all sorts of things they tried to do in order to stabilize that, to keep the soils from combining with water, to extract the water, to get the water to come out before it started sliding down the hillside again. Yeah, that's some of it. Yeah. Yeah. Yes. Yes, I do. Can we wait till we have a sort of break? Okay. All right. So that's hydration. Any kind of combining with water, which could be dissolving in water or water just combining with the material and creating some type of chemical weathering. Let me erase my scratch there. And here's a couple of pictures you do see in the text. I'll look at this and say, what does that have to do with chemical weathering? Well, guess what? This is limestone. And the limestone has been eaten away by water. Now, when we have rainfall, I mentioned anytime you have lightning, you have nitrogen combining with oxygen, forming nitrous oxides. That combines with water, which rain usually accompanies thunder and lightning. And then you have some nitric acid. It's really weak nitric acid, but just about all rain is slightly acidic. Either carbon dioxide mixed with water, nitrogen oxide mixed with water, sulfur oxide mixed with water, you got acid rain. Now, if you've had a lot of companies pouring a lot of carbon into the air, carbon dioxide, like plants, okay, and you've also been burning high sulfur fuels like coal, gasoline, diesel, you have sulfur, you're putting more oxides in the air, and when you put more oxides in the air, you get more acid in the rainfall, and they call that acid rain. All rain is somewhat acid, but there were areas, I think Pennsylvania, Ohio, some of that really industrialized areas, putting lots of stuff in the air, also got plenty of rainfall. You had whole forests losing their leaves because the acid was too strong for them to live. Yeah, and it will, absolutely. And the over in Europe, Soviet Union was notorious for pouring out lots of pollutants in the air, and whole stretches of Poland and some of those other countries had almost completely denuded their forests because it killed the forests there. And you talk about, what's that?
Do it hurt you if you follow him?
Actually, if you have sensitive skin, it might. I have a, say again?
What about their drinking?
It's no more acid than a Coca-Cola or a soda, so you won't notice anything. Okay. You know what your stomach is?
Well, then how can it do a whole forest? But
Because those trees may be, okay, think about your digestive system. Where is some of the strongest acid in the world? In your stomach. That's what breaks down food. Your stomach is lined with a really strong organic thing that protects it. If you get a weakening in that coating, you get ulcers. Exactly, because the acid gets through to sensitive tissue, okay? So your stomach, you already have really, really strong acid in your body. That's what breaks down food, and that's how we digest. But then it gets neutralized as it moves on down through the gut and stuff. So it doesn't bother us as much as it would a tender little tea leaf, on the plants. So it eats away at the rocks too. So all this breakdown that you see here, probably from acid rain. Okay? And here's what they were trying to show, and I don't think it's particularly clear. You have some little limestone caves in here. You probably have a hard time seeing them, but there are little caves in there because that's been washed away. Now, I've never been to them, but there's some really famous caves out west. I can't think the name of them, but I believe that even up in Alabama in the Soda Caverns, do they have those? Yeah, but do they have the stalactites and stalagmites? Yeah, exactly. That is limestone that's been dissolved in water, and as the water is dripped and then evaporated, it leaves the ones hanging from the ceiling, or when it drops on the floor, it builds up the ones that come from the floor. That's limestone, okay? And that's acid water has eaten away there. And that's largely what's happened here. This river is cut through. Now they're suggesting this is limestone. I don't know for sure if it is, but that's what makes these. That's part of the action of the river. Part of it is physical, part of it is chemical. Hydration, acidification, probably not too much, but it could be even some oxidation. It's all acting together. And remember those tiny little root hairs? They're secreting acid. That's chemical, okay? And that's what breaks down the rock. That's where the trees or the plants then get their minerals from the soil and take it up with the water. And now the soil particles have been broken down even more, or the rock has been broken down anymore because of that acidification. So biological weathering, chemical weathering, and even the wedging of the physical weathering, they all go together. It's not that they're separate. They all go together. The water moving through there, the motion of the water is physical. The hydration and carbonate acidification, that's chemical. And if you have things growing on the rock, the lichens, the molds and mosses and things like this that grow on rock, they're eating into the rock and they're breaking it down. What do they call the northeastern schools that are really snobby? The Ivy League school. Where do they get that name?
From all the ivy on their building.
Ivy on the buildings, exactly. Oh, it makes it look so, special. Guess what? A really bad idea to have ivy growing on buildings. How does it hang on to the building? It has little things like roots, fiber that go in, and they secrete acid, go into the mortar, and start breaking it down. So after a while, no more mortar. You have sand in between the bricks. Not a good idea. So look. What's that?
Is that a northeast thing or something? Why are Ivy League schools in the northeast?
Well, they built the buildings with brick buildings. They had a lot of, clays and stuff to do it. And I guess the conditions were good for ivy, and they just thought it looked cool. They may have even planted ivy. Not a smart move. Okay, not a smart move at all. Okay, but it looked cool. It made them seem special. Okay. Now, they left off the biological weathering. The biological weathering is that created by plants. Like I was going to say, the lichens, the mosses, and stuff like this, they're the first things that grow on rock. And as they grow, they break down, they secrete the acids, they break down the rock material, and that makes soil. So now we're getting to our soils. This is the place I love. This is my background with soils. I grew up on a farm, and I was in soils in graduate school, so in agronomy, soil science. What soils are, definition, mixtures of unconsolidated, unhealed. He's here. Now, what does unconsolidated mean? Unconsolidated. Not together. Here's the word solid in there. And Con means with, so the solids are not with each other anymore, they're unconsolidated. They've broken apart, okay? So these are the smaller particles that used to be rock, they're the particles, weathered, and that could be weathered from mechanical weathering or physical weathering, from chemical weathering, or from biological weathering. Any of those earth materials meaning it was originally rock. And here we have our humus. What is humus? Definition within a definition. The altered, decay-resistant plant material.
Bean dip.
Huh?
Bean dip.
Yeah, okay, that's hummus. Don't be putting humus in your hummus, okay. Okay. A lot of times we'll say, oh, that's really rich. What? When you look at a soil and say, oh, that's rich soil, what makes you think that? What about the color?
Full of minerals.
Oh, a dark, rich looking. That mostly is humus. It has fairly little to do with the soil, and surprisingly little to do with the nutrition of the soil. What it does for the soil is make the soil hold moisture better. And if there's plenty of moisture, then more minerals can be dissolved in the moisture, and the plants thrive in it because they have plenty of moisture. It's not that it's all that rich. There can be a little bit, but most of the time it's just the ability to hold moisture. We'll talk about that in just a minute too. So humus, that's altered, decay-resistant plant material. So when you see little leaf particles there, that's not humus. But when those deteriorate away, they'll turn dark, and that is really a sort of a gelatinous substance that coats the soil particles. Just like those iron oxides are on the surface of the clays, humus is on the surface of the other soil, clays and other soil particles. And that humus is really what makes that a good growth producing soil. Okay? Now, what are those weathered earth materials? The weathered materials include your quartzy sand, the stuff that's gritty, that you can feel with your fingers. That's sand. It feels rough. Almost no nutrient at all in quartz. I mean, the plants are not going to get anything out of quartz that are beneficial. But you need them to hold soil in place. Clay minerals. Clays, on the other hand, are so tiny you can't see them with a microscope. You have to have an electron microscope, and they're submicroscopic in size. And because they have so much surface area, they tend to attract and collect water and nutrients. Okay? So clay minerals are usually good to have, but on the other hand, clays are hard to manage because they can get so hard when they dry and so slick when they're wet. They compact so badly, they're just hard to deal with. You also have the metal oxides which coat the clays, like the iron oxides and others, and you have salts that tend to be sometimes good as fertilizer salts and sometimes bad when they're sodium chloride salts, that kind of salt. Plants can't use that much of that. So what is it that humus does? Well, let's say we have a sandy soil. What's typical of a sandy soil? Water runs through it like crazy. Okay, yeah. If you got a sandy soil, it rains hard, it just goes right through it. Okay.
Yeah, I put sand in a plant recently, and I almost killed it because the water wouldn't retain any moisture.
Exactly. So what do? You add humus. You put leaf molds and stuff like that in it, and now the humus coats the sand particles, and guess what? They then hold on to moisture, and you can have much more growthy type soil.
Did you say leaf?
Leaf, yeah, like compost. Yeah. Anything that would be compost. Okay? Manure is good. Microorganisms love manure, and they're in manure, and they help break down and make that humus. Okay? Say again?
I was talking about what we eat, GMOs.
Oh, yeah. Oh, GMOs, yeah. Genetically modified organisms. Okay. Actually, just about everything is genetically modified organism. Well, not genetically, maybe, okay. But we got lots of modified organisms. Okay. But let's take a clay soil that hangs on to moisture so tightly the plant roots can't compete with it, because it wants to really hang on to it. So what do? Add humus, add that mulch, add that compost and stuff like this. Now that coats the clay particles, and now they become much more, they allow water to flow through more easily, and the plants don't have to compete with the strength of the thing. So humus is going to improve any soil. Okay. The trouble is, down here in the south, in January, we're probably going to have more hours of the days that are above 40 degrees than we have below 40 degrees. And when it's above 40 degrees, all that stuff is decaying. Up north, in some places the soil never gets above 40 degrees from November through February. Okay, never, because it's coated with snow and ice or just really cold temperatures. So all your chemical activity that's deteriorating that humus is not happening. So you build it up, it stays all winter, and you use it the next spring. Down here, it oxidizes away very, very quickly. Okay? So, and they mentioned sands and clays. You also have silts, but there's not nearly as many silts as there are sands and clays. Now, the best type of soil in general is what they call a loam. Now, in soil science, they have what they call the soil triangle: sands, silts, and clays. Okay? If you have a totally sandy soil, it's not going to hold moisture, it doesn't have hold nutrients, plants aren't going to thrive in that. If you have a totally silty soil, not particularly great soil either. Totally clayey soil, not so good. You need a good mix of all of those. So a loam is right in the middle of that triangle. It's a soil containing varying amounts of sand, the coarse stuff, silts, the medium stuff, and clay, the very, very fine stuff, mixed with an abundance of humus. That mulch, your compost, that type of thing. Plenty of that, you're going to have a great soil. Now they say that's also known as topsoil. That's not really a good definition of topsoil. Loam is a type of soil. Topsoil is the top layer of the soil. No matter what, it could be a sand, it could be a clay, it could be whatever. That's what topsoil is. Your loam, you want that to be your topsoil because that's where your plants are going to grow best. But what a loam is that mixture. You're in the middle of the triangle. Okay? Good clay, sand, and silt content, so you have a good mixture. See, what that allows, it all gets down to pore size, basically. If you have a sandy soil, those are big particles of soil, meaning the pores are large, and water runs through them too quickly. If you have a clayey soil, your particles are tiny, so your pores are tiny. And now the water can't even infiltrate the soil because it takes so long for it to make its way through the soil. So it puddles, okay? Most of the time if you have a puddle in your driveway, that's a clayey soil, okay? Because it just does not infiltrate. And what's more, you run over it, pack it down, and clays are basically sheet silicates, and they pack down and squeeze out the water, and now nothing penetrates them. So that's why puddles happen, okay? And then the silts are kind of in between. But if you have a mixture, you have some large pore sizes, some small pore sizes. So the soil retains some water, but also allows the drainage to happen. So it doesn't puddle, but it doesn't all run through. So that's why you want a good mix of sand, silt, and clay, so you have a mixture of pore sizes. And the more humus you have in it, then the more that's able to retain moisture as well on the surfaces of the soil particles, and it also retains nutrients there too.
they sell topsoil?
Yeah, and that can be anything. It really irritates me sometimes to go to Home Depot and buy a bag of topsoil, and I get home and open it up, and what it is the residue from a pile of mulch. Exactly. It's hardly any soil at all. You know, it'll evaporate away. Or, and I've seen this happen too, it's a sand and they burn something on it, so it looks nice and dark, but that's just because it's the soot that's left over mixed with sand, and that's almost worthless. Okay, so
You apply loam there. You a gardener, you know, and you want.
no, you don't apply loam. Loam happens. Okay,
You can't acquire it. You can't get it to your garden. Or
you go to a field that has a good mix of those and get your out buckets off it. The farmer probably won't like you very much. Okay, yeah, no, that's just it's a mix of all three. Yeah, and.
I keep a thing of soil and a thing of sand, and then that little white.
Vermiculite.
Yes, I'll keep all that. The only thing I don't have is the mulch.
Right.
Because that's.
Peat is used quite often.
It's easy to do thing.
Yeah.
What are you doing with it?
I like plants, house plants and
Keep
stuff.
Never mind that. We're not one of those states yet. Okay.
Yet.
I'm voting.
Okay. All right.
If I could, I would.
Yeah.
Sure would.
Actually, when we first moved into the house we are now, and we needed some things, my wife did exactly. She found the recipe in Southern Living or somewhere, and we bought bags of sand, bags of peat moss. There's something else we put in it, and then we put a little bit of lime, and we put a little bit of iron sulfate, and you mix it up to make your own soil. A little different from grow your own. Okay. You should know what I'm talking about. All right, why do you laughing? Okay, so topsoil is whatever you have on top. Now, here's the sad news. When I think I told you, or maybe not. I've taught this course so many times I can't remember what I've told y'all and what was the previous one. Have we talked about the glaciers pushing? Bulldozing. But they also bring with them soil. And when the glaciers came down from Canada into the U.S., they brought lots and lots of soil embedded in the bottom. And then when they melted, they retreated and left that soil. So in our Midwest, Nebraska, Illinois, Indiana, they measure topsoil in feet, not inches. Down here, centimeters. You got it. You know, topsoil is very, very
This is not a
thin.
good state to grow anyway.
Yeah. But it's better in Georgia because we're underlain by limestone, whereas they're underlain by granite. But you see, we over-farm like crazy here. We lost a lot of our topsoil. So what we are counting topsoil now used to be subsoil, you know. So topsoil is whatever that top layer is. The subsoil is whatever is beneath it. Now they say it's less fertile. It usually is. Okay. Ashlyn is here. All right. The main reason it's less fertile, I would say, is because there's less humus in it. Because humus usually collects at the top, and it doesn't usually make its way very far down. Whereas in the Midwest, it's just amazing. Well, if you think what the Midwest was, it was prairie. And what prairie was covered with was these great prairie grasses. And the great prairie grasses, because they're a little bit dry, the root systems on those grasses, I mean, were massive. And they went way deep mining for water and nutrients and stuff. So they would go feet down, you know, the roots would. Okay? Well, then every winter, they die, and all those roots go into the soil, adding humus right there. So you have that. And then the next spring, they produce new roots, you know, and stuff, And so they keep really deep, nice soil. I mean, they measure them in feet, and they go into a field and just bulldoze, because they may take some topsoil from here and moved it down here. Well, they still got a few feet here and many feet here, and they level it off so they can irrigate. They just do whatever. You couldn't do that in the southeast. You go down anyway, and you're in the subsoil. You can't even plant there. It's hard to get your equipment together. So it's less fertile, mostly because of that humus is not there to hold the nutrients. It doesn't hold moisture as well. Contains more rocks and mineral accumulation. Now that may not be totally bad, because that's where the minerals come from. That's where fertility comes from, those rocks and minerals. But they're in chunks. They're not broken down. They're not weathered, so the plants can't get to it. And the big news is it contains less humus. So it doesn't hold moisture as well and doesn't hold the nutrients as well. That's why it's less fertile. Now, I don't like that they related loam to topsoil. You want loam in your topsoil, but loam is not topsoil. Loam is a mix of soils. Okay. Now, you ask how you can do loam. If your soil is really clay, then get sand and mix with it. Okay. If it's really sandy, get you some clay or humus and mix with it. Yeah, you can make your own loam by mixing other things with it, but it takes huge quantities to do so. But for your root depth, you can usually do that. And that's what you do in beds and things like that. For a field, it's fairly impractical to change the soil. But for a potted plant, you can do that. And unfortunately, they have one slide on soils. Shame on them. Okay, that was 20.3. 20.4, okay? This is erosion, the bad stuff, okay? Erosion is the mass movement of soil, okay? Mass movement of soil. Erosion is caused most of the time, not all the time, most of the time by gravity, directly by gravity. Gravity. Ever see Wicked? No, never mind. No, okay. If you think about this, I want to go all the way back. What created that valley, Grand Canyon, or the canyon at Yellowstone? Water rushing through. Well, what was water doing? Why was it rushing through? It always goes downhill. Gravity pulling it downhill. Okay?
I would think more along the line of water, air,
okay. Yeah, and we'll get to those. But water moves because of gravity. It doesn't move any other way. Wind moves with other reasons. That's why I said it. So yes, wind causes some erosion, but it's minor compared to the other. But not all of it is water pulling. I mean, what is a landslide? It's mud and rocks and everything else being pulled downhill by gravity. Gravity causes most of your erosion. Okay? Now, two types. Now, we're not getting into the water yet. Just the movement of soil. If it's moving slowly, it's called creep. Okay? And I can remember in a lower level school, maybe beginning of junior high or something, and I think it was a science or sociology, some sort of class that we had, and they talked about the farmers in Europe that were in the mountainous regions, how they would go in the early days and always get wheelbarrows load of soil from the lower part and carry them up to the higher part, because gravity was always pulling it down, so they would move it back up so they could not lose the soil down the hillside. That soil creep, slow movement down a steep slope. If it's moving rapidly, that's a landslide. Okay, you can tell when a landslide is happening. It's also called an avalanche. Okay, and it says slow to rapid movement, but obvious movement. This one you don't see or sense; it just happens so slowly. But a landslide is any slow to rapid downhill movement of material, as in an avalanche or that type of thing. Now, avalanche can also, and sometimes is related to snow, but this is talking about not. Now this, I've never noticed trees doing this. This author is from Arizona State. He's a Western guy. I bet you on the slopes of the Rocky Mountains, you'll see this kind of stuff. You'll see trees doing this. What the tree's trying to do is reach the sun. Yeah.
I was just gonna say, yeah, I've seen trees do that where they, well, maybe not exactly like
Yeah,
that
not
up
this
right,
much.
but I have seen them
Right.
truly in the mountains where
In the mountains, yeah.
the trunk tilts and some of the branches kind of tilts, but the
Yes,
rest of it-
exactly. And I'm saying it does happen. I just don't see it much around here. But if you've been in the mountains, you'll see this. Maybe not to that extent, or maybe you will. But see, the tree is always going to try to find the light. So it's trying to grow up, but if the soil's moving out from it, it still tries to grow up. Okay? And so, what's that?
The one at the bottom of the left, did not see.
Yeah, I know. And frankly, it almost looks backwards to me. It would almost seem like it would be moving the other way. The curve would be downhill and it would be doing that. But maybe this is what they do too. I don't know. I've not seen it enough to know whether they cut the orientation right or not. But
So what they saying that the soil making
yeah, the soil, the tree started like this, and as the soil moved, it must have its roots in here, but the soil is pushing it this way, but the tree's still trying to grow up.
That's the same tree.
No, well, no, I don't know.
Different
It's a
trees.
picture. It's not reality.
I mean, that's the same tree, or the tree moved all the way down.
No, this is different trees at different locations.
Oh,
That's
okay.
it's the same tree. I think it's the same. That's what I think. The tree just slid down. I mean, the progression of the tree. It started.
But if that were the case, then it should be a smaller tree, and then it's growing, but also going downhill. So I don't.
That's what you teach. That's
No,
right.
no,
That's
no.
right. You need to write books. Yeah, you need to write textbooks.
Hey, I can hardly write an email, so I think. Okay. Okay. And by the way, before we get off of it, there's a little concept supplied about city weathering. What? What are they talking about there? Well, if you have seen a building that has limestone in the facade of the building, it might look really nice and pretty for a few years, but guess what? It's going to get pretty dingy looking fairly soon. Couple reasons for that. Acid rain is going to pit that limestone, number one. In the pits where it starts wearing away, then microorganisms grow there. They get black and moldy looking, and after a while it really, so they go in and pressure wash it and stuff, and it'll make it look good again, but all the time they're taking off, they're weathering that limestone, okay? Yeah. What's that again? Yeah, but all that is weathering. That's biological weathering, chemical weathering, physical weathering. Now, how else do they clean buildings? We're going to talk about this a little later. Sandblast them. Guess what? You're eating away the surface. You're just getting the dirty surface off and getting the surface underneath, and soon that will be dirty again. Second, I don't know if there is a good way to do it. The chemicals will do it, will eat it away, and the sandblasting will. So I don't know. I think probably the best thing would try to coat it with something to retard it, and therefore you don't have as much. But that's pretty expensive too. There's actually a house, when I drive to work just about every morning I pass by it, and it has I guess it's a chimney type thing, or maybe just a facade there, and you can see the part that's under the porch, and that's pretty well protected, and then the one that's up above the roof line, it's the same stone, you know it is, but above the roof line, it's ugly. And beneath all, it's just really pretty. You know at one time it all looked that nice, pretty, bright colored stone. And, fresh looking. Now the upper part has weathered. Oh, and what you were talking about before, I meant to do this, and let's go back to it now. I have a Toyota vehicle, so I take my vehicle to Jim Limbaugh for his usual maintenance and stuff. The old guy that almost always gives me a ride, to work then when I take it in the morning, he has been in Birmingham forever, it sounds like. And he has worked in all sorts of areas. And he told me stories when we'd be riding along, of back when the steel mills were really going big time. I think it was on certain mornings they would blow the furnaces. They would put hot steam in them and maybe a little bit of clean out the stuff that's built. And he said the ladies knew not to have any clothes on the line that day. Because when you mentioned the sulfuric acid, that's what made me think of it. You would burn holes in the clothes. You would have dirty clothes, dirtier when you brought them in than when you put them out. He said it was terrible what the air was filled with back then. Now that, well, of course, they don't do nearly the mining and the processing of materials they used to, but also they're much cleaner about it. But he said in the old days, you did not. And you mentioned your cars. So if you didn't have a place to put your car under, you're going to get new cars pretty frequently because it would eat away the paint, it would rust it, corroding. Those were chemicals coming out of that stuff. Really bad chemicals. Chemical weathering, man-made. Okay. This picture is in your book on page 511. Again, the examples they have here are dealing with gradients and slopes, stuff that you would have done in the first half of the book. We haven't done, but they really don't contribute much to what we're talking about here. But if you want to take a look at them, it is pretty good. Okay. And they're talking here about displacement of tombstones by the process. If you have a graveyard on the slope, you can actually measure and look at the dates on the tombstone and see that the older ones have moved down further than the newer ones have. It's a pretty interesting little example there too. Example of soil creep. Now, how much did they find? 0.54 millimeters per year. Okay, remember what a millimeter is? A dime, the thickness of a dime. Let's see if I can. Yeah, there's one. Okay, 0.54 is about half a dime. So it moves half a dime a year. Thickness of a dime a year. You're not going to notice that until 50 or 60 or 100 years later. Hey, that thing moved a little. Yeah, 5 dimes worth. Yeah, exactly. All right. Making fun of my analogies. Okay. Now, what are the things that create this erosion? There's mass movement just pulled by gravity. That was one. But now the big one. And this is caused by gravity, running water. This is the most important of all the gravitational erosion processes. The creep, now, yeah, landslides are major when they happen, but they don't happen that frequently. But water's always moving. So the most important of these 3 stream processes, okay, mechanisms. Number 1, the water dissolves materials. Okay? The minerals, the nutrients, whatever it is that was there, maybe it's those cementing agents, it's being dissolved by the water. So now it's not held together as tightly. Okay? The water also, when it's moving, suspends material. Now, what's the difference in dissolving and suspending? Okay. Let me do an example here. Do you mind if I pick this up? Okay. You notice this? You can almost see through it. It's mostly almost transparent. It's colored, of course, but you can see through it, right? Yeah. There's so much paper there you see. You can see through it. That's mostly dissolved material. If you have milk, you can't see through that. That's suspended material. The calcium's suspended in there, the fats are suspended in there, everything's suspended. If you can see through a liquid, that's usually dissolved materials in there, like salt water, sugar water. Yeah, you can see through it. Tea, okay? But orange juice, not, okay? The things are suspended in it. So dissolved materials, that's actually a chemical process solution. Those hydrogen bonds are breaking the salts apart and dissolving them. Okay, yeah.
That's why, like you said, milk and orange juice is suspended material. In time, if you let it settle, things settle.
It definitely will.
Yeah.
It definitely will. You let that sit, it can sit for days and days and days. It's still going to do. Now, if there is any suspended stuff, that may cut the bottom a little bit, but most of it stays just like it is. Yeah, good example. So you have dissolved materials in water, you have suspended materials in water, that's in the water. Or the water may be moving so rapidly, it's carrying with it material, like sand particles, like gravel, even boulders sometimes, if the water's moving fast enough and hard enough. And that rolling, bouncing, sliding along the stream bed, that's breaking up all the materials, and that's being carried. So it just builds on itself. Okay? And then, where does this fit in? This should be a separate slide. It is the next slide. Stream bed evolves over time. That shouldn't be here. It should be the other place. So let's turn and look at that. Okay, before we get to that, though, here a rainfall has just happened. Okay? Heavy rainfall, it looks like. Now, it looks like the soil was well covered with vegetation. But still, the rain came so heavy and thing. What do you think is in this water? Is that pure water? No, you have a bunch of suspended material in that water. It's gotten clay particles, maybe even some silt particles, maybe even where it's running real fast, some sand particles are coming down. And certainly you have dissolved stuff in there, and that is going downhill due to gravity. So you're eroding. That is eroding big time. In fact, that's why this is coming out here, because this was soft material here than it was here, and it's eroding that, making the gully. Okay? Now, we're still not at stream beds evolve over time. Ha! This follows. Oh, did y'all need that any longer? Okay. So, the stream bed evolves over time should be the title of this one. Okay? In a young stream development, say the landmass is recently uplifted, you've had geological things going on. And when you say young, this is only thousands of years, okay, as opposed to 10,000s of years or millions of years. So this is young. The landmass recently, like in the last few thousand years, recently uplifted. The stream gradients, meaning the kind of the fall over, on a rooftop, you talk about slope or pitch, rise over run, like in math. When you talk about slope, well, gradient is kind of going the other way. Drop over run. If it's real steep, that's a great. This would be less. So the steep gradient, and you tend to have V-shaped valleys. Generally, no floodplain down at the bottom. It's just moving water. Okay. Think of the Yellowstone River. Below that thing. That was a V-shaped valley. They just went down like this, and the water rushed by. There was no pooling down there at all. There are boulders, rapids, waterfalls. You saw the waterfall up there, okay? Down below, I bet you whitewater rafting. Great for that. I'm not going to go on one, but anyway. Now, the more mature landscape, what did happen? You've eaten up the soil up here, carried it down here, build it up here, eating it away there, so now your gradient is less. Before it was like this, now it's like this. Soil from up here has gone down here, and it took the slope out of it, or some of it. The stream gradient is smooth and lower. Now the stream doesn't rush downhill, it sort of meanders. You do have a floodplain that it sort of wanders. Take a look at a map of Louisiana, Mississippi, where the old Mississippi River flows down. I don't know what it's like. My brother and his wife took a trip It was his 60th birthday. Their vacation, or his retirement place, something. They took a trip on the Mississippi, and that must have been something because the Mississippi does this. Near in the southern part, I mean, it backs up almost on itself. Take a look at a map of it sometime. It's amazing. That's what we mean by meander. Whereas upstream, probably at the beginning of the Mississippi, are probably going pretty fast downhill. When the stream gradient is lowered, it kind of flows wherever it wants to. And in the old age, very low gradient.
Oh, yeah.
Okay, we don't know anything about that. Okay, broad, gently sloping valleys, sluggish flow, more floods. That's your delta. We're going to get to that in a minute. So here's the pictures illustrating this. The use of the landscape, when you have the erosion, it happens dramatically. The water runs downhill pretty quickly. It cuts V-shaped valleys. You have peaks here. Everything is new, fresh, clean cuts. In a more mature landscape, the mountains are sort of smoothed out some, or the hills have. The water now doesn't go as fast. It moves around some and meanders a bit more. And in the old landscape, hardly any hills left. And everything's almost a floodplain. And when you have a great amount of water, the whole thing could flood. Now, interesting thing here. You see this? That is sometimes called a bow lake. Now, how did that bow lake form? At one time, this river probably came this way. And something changed. Something ate its way through here, so it quit going that way and went this way. But that low part there is a bow lake. Yeah.
Man-made a lot of time.
They could be. They could be. But my wife's brother, they live in Alexandria, Louisiana, but they have a camp house or something on what they call Cane River Lake. Okay? Cane River Lake. And what it is where the Cane River used to flow, but then it changed its course and left the lake there. And so they're on that Cane River Lake. When Karen had meetings in Lake Como, Italy, which is real close to Switzerland, northeastern Italy, there was one of those weeks in between terms, so I got to go with her, sightsee. Actually, our niece went with us too, so she and I were sightseeing. And Lake Como is a beautiful lake, but it doesn't have an outlet. It's a dead lake almost. They say, do not eat any fish you catch out of it. There's two other lakes, they have flow through. But this one, something in the geology of it, it's a backwater lake. And it's not a beautiful lake. People have houses around it, but just don't eat anything out of it, they say. I'm sure some people do. But yeah, some of them are man-made and some of them occur naturally. I'm pretty sure Lake Como naturally occurring that way. But the water flows in, but it just sort of seeps out. There's no really good outlet. So you don't have, in other words, sort of the overflow goes there and then it goes to the fresh water goes to the other way. Only when so sometimes you're right. Men can do this, dam it up and do that. But other times nature did it herself. Over long periods of time. But again, look at a map showing Louisiana, Mississippi, the Mississippi River flowing in between. And you'll see a bunch of those bow lakes, just scattered all through there. And the river just still going like crazy. Okay, and this again is that picture. What kind is that? Youth, maturity, old age.
Yellowstone.
That's Yellowstone.
I said sandstone the first time.
Yeah. And what kind is that? Youthful, mature, or old age? That's useful. Look at that V-shaped valley, waterfalls, steep gradient. Talk about a steep gradient. That's almost directly down. And even down here, still no pooling, no floodplain. It's just running like crazy. Very much V-shaped valleys. because Yellowstone's a fairly new geological formation, maybe only a few thousand years old. Okay, that's new, useful. Whereas Appalachians, who knows how old they are? Okay, very rounded hilltops and stuff. Okay. Now, let's go on downstream a little bit. Let's see, they do have a few other pictures or any worth looking at. There is a little blurb in the book, Concepts Applied, Creeping Trees. Not different from creepy trees, but creeping trees. Okay. And you'll see a picture there of moving streams of water carrying lots of dissolved and suspended materials. That's largely suspended there. And you see that erosion has happened. You know that. Here is a, I don't know if y'all can see it. If you got your books, look in your book. Here's a river that's running through here somewhere. There it is. But look at this. You can almost tell that at one time this probably was where the river went. It had that bow in it. I can't tell that, maybe it's that paper or whatever. But you see, that's sort of meandering. This is a more mature, or if not old age landscape. There's lots of floodplain. Okay. Another pretty picture of the Yellowstone Falls. As they say, I don't know which this is. That looks more like the lower falls. I may be wrong. Okay. So, deltas. That follows from the floodplain. This is on page 514. It's not a subdivision, but it's a highlight, bold word in the paragraph. What is a delta? It's a triangle. No, that's a different. Deposits of sediment at the mouth of a river or stream. So this is in the part way down, right before it's going to flow into wherever it flows into, where it's a fairly old landscape. You've had years, if not centuries, of sediments coming downstream, being dropped off, and now it's just sort of filled in. The stream flow dissipates into an ocean or a lake, or the Gulf of Mexico, for instance. The erosion and sediment carrying abilities have been lost, so now those sediments, the suspended materials, fall out. Okay. You'll even see this in stream banks. In fact, it's sort of interesting to do sometimes. If you have a place where water flows in a big curve like that, okay, the water's moving faster on this side and slower on this side. Yeah, on the outside it's moving faster, slower here. So the slower water is going to drop out the sands faster, and on the outer side it's going, the sands have already dropped out and you'll carry clays more. So quite often you have sandy soil on this side and clayey soil on that side because of sedimentation. Almost centrifuge effect. Okay. So a delta is like that inside area where everything is sluggish. Okay? And what has happened, and this is a picture, they don't say where that is, I don't think. That particular picture is not in our book anymore. It's in the older edition. But you can tell, I bet you the beach at one time was back here. But over time, more sediment has come down, dropped out, and the water slowed down, and it's built up layer on layer on layer on layer. And there was the old beach back here, and this is all new land here. Okay? What's the... Yeah, close. Okay. It's hard to see here. But you know what that is right there? Sort of sticks out into the Gulf. Louisiana. That's exactly. I would guess, I don't know what percentage of it, I would say probably close to 10% of Louisiana used to be up here somewhere. Okay? because it's run down the Mississippi, Missouri Valley, Ohio Valley, all those lead into the Gulf of Mexico, and it carried eroded soil all the way. And when it slowed down, it deposited and deposited and deposited, and all that sticks out there is delta. It used to be upstream somewhere, soil that was washed away and has been deposited there. We call these the wetlands, and there's very few more important things in our ecosystem than the wetlands. Do we need to take a break? Seems like a lot of people are. Let's take a quick break. We'll come back and continue to talk about deltas, and basically what these are caused by deposits at the mouth of a stream or a river, where the erosion has been carried downstream, and when it slows down in that, floodplains and stuff, then the sediment falls out, and it builds on it and builds on it. I guess these are okay. I would have these a lot flatter looking, okay? They're a little too steep like that to me. They should be flatter, and it just keeps building and building and extending further out. And like I said, I think a good portion of Louisiana is probably delta that is washed down from, most of the U.S. We'll talk about this in the water chapter, the last chapter we do, how big of a, what they call a flood, watershed the Mississippi is. Way more than, I think, like 2/3 of the continent flows into the Mississippi. It's amazing. Okay, maybe not like that, but an awful lot. Okay, and when it slows down, the erosion and sediment carrying abilities are lost, so the stuff settles out, and you form new land masses. Now, these are your wetlands, and the wetlands are filters. They are tremendous parts of the ecosystem. Now, what we tend to do is try to modify them and make things run faster through them and do things. Not a good idea. Nature has a reason for them being there, and they do a tremendous job. Now, when the Gulf oil spill happened, and a lot of these things lost some vegetation and stuff, they quit doing the jobs as well. Lots of plant and animal life live in the deltas, okay? Enormous diversity. And when you get pesticide spills upstream, sometimes that wipes out populations downstream. I'm trying not to make this very political, but it's hard not to. There's a popular phrase that happened in the last year or so of drain the swamp. Okay? And frankly, what I think I see happening is they're draining wetlands and replacing it with toxic dumps. So I'm sorry, I shouldn't get into that. But literally, wetlands and swamps do a tremendous service. Not politically, but and whenever we start messing with them, we really are treading on some thin ice, sort of, about damage we could be doing to the whole ecosystem. All right. Now, we talked about gravity pulling soil downhill. We call that soil creep or landslides. Okay? We talked about gravity pulling water downhill. And that's the biggest form of gravity-induced, in fact, any kind of erosion is from water moving under the effect of gravity. But water isn't the only thing that does. Glaciers are pulled downhill by gravity. It's just the rate at which they move is slothfully slow, okay? Very, very slow. Masses of ice, which, by the way, is water, it's just in the frozen state, phase, on land that move under their own weight because gravity's pulling them downhill. And they are always moving. You never notice, it's a lot like soil creep. You never see them move, but you know they move. They form from snow accumulated over a number of years. Now, some glaciers, the newest glaciers, I don't know if many of these, could be as few as 5 years old. Snow accumulated over 5 years. Many of them are over 3,000, 3,500 years of snow accumulation. That's a lot of snow. Okay? Two different typical classifications for glaciers. Okay? Now, one name comes from where they were first named and identified in Western Europe. What major mountain ranges in Western Europe? The Alps. So they called those glaciers alpine glaciers. They could be anywhere. They could be in the Rockies. They could be in Australia. They could be in South America, but they're called alpine glaciers because whoever named them in our background was from Europe. Okay? They form at very high elevations and they flow down valleys. Okay? So therefore, the better name for them would probably be valley glaciers because they're not just in the Alps. They're in valleys wherever those happen to be. Okay? The second kind is called the continental glaciers. These are great sheets of ice that move downhill very, very slowly. Cover a large area of a continent. Today, they're largely in Greenland and Antarctica. Now, my wife's family used to like to take sort of big trips about every 3 or 4 summers. They just enjoyed planning them for long periods of time, and when we could all get off, then we'd go on one of these trips. And we went up to British Columbia, Canada. That's north of Washington State and before you get to Alaska. And there is an area there, it's one of the closest big towns is Jasper, but it's not Jasper, Alabama, but it's Jasper, Canada. And they have what they call Columbia ice fields. And that was probably a smaller continental glacier, but just a big sheet glacier. Okay? That had first been discovered by European-type people around 1901 or somewhere around that. I'm sure people knew about it beforehand, but we didn't know about it beforehand. So someone put a stake down when they first at the foot of that glacier. From that stake, you don't even see the glacier anymore. You have to walk upstream, you might say, that's not the very thing, more than a mile before you get to the glacier. That's how much the glacier has retreated in a little over a century. Not a good sign, okay? No global warming happening. Okay. I don't believe it. Okay. So, but the bigger ones are in Antarctica and Greenland. And most of them are retreating or falling into the ocean too. There's still a lot there. We'll talk about this more in the chapter on waters, earth waters. That's 24. We'll get there later. Now, what kind do you think that is? Say again? Okay. What kind of glacier? 2 kinds of glaciers.
Oh, continental.
You think that's continental?
Yes.
That's alpine or valley glaciers. It's in the valley between mountains. The continental glaciers are the broad. You wouldn't see any mountain peaks, okay? And you can see this valley was way back there and down here and down here, and it's moving downhill. You don't see it move at all, but it is moving slowly under its own weight. Gravity is pulling it down the valley. Okay? That's the valley glacier or alpine glacier. Okay. 3 mechanisms. They love their 3s, don't they? For these for glacier erosions. Okay, and we talked about this earlier. The first of these is the bulldozing effect. Because these glaciers, you don't see the end of this one. It's somewhere out of the shot here. Wherever the end of this glacier is, it's moving down. It's almost a vertical sheet. And it may go way, way down. Okay? A lot of weight to it, and it's moving downhill. So anything in front of it gets pushed in front. That's what we mean by bulldozing. Okay? Forms deposits called moraines. that is being pushed ahead of it. And as long as the glacier is going downstream, it's pushing this ahead. Now, whenever that stops, okay, and starts retreating, all that rock material and soil material, other things that got pushed down, it stays there. And now it forms a moraine, okay? Now, if that was in a valley, then that has just formed a big dam. And then the glacier melts and the water fills in behind it, as long as there's a place for that to happen. One of the prettiest lakes when we were in Canada was called Moraine Lake. And you drove up to it and you saw these just huge boulders just laying at all sorts of angles and stuff. You think, who put these there? No one put them there. The glacier pushed them there and just left them. They're just jagged, and they're different kinds of rock because it picked them up probably over miles and miles. But then when it started, after the last ice age, started retreating and melting, that was a good enough dam that the water backed up in there. So behind it is this beautiful lake called Moraine Lake.
So have you been to Alaska?
Not to Alaska. I really would like to go. I hope maybe if we can afford it when I retire, we'll make a trip to Alaska. Have you been? They say, yeah.
When are you retired?
I'm 66 now, and as long as my health holds out and I feel good about enjoying what I'm doing, I hope to go to 70, but not much past 70. Yeah. So maybe 4 more years. Huh?
I say you doing good.
Well, I feel okay, so I hope so. Okay, a second way that glaciers erode, second mechanism, is abrasion. Okay, if you can imagine, can I go back just shortly? This glacier, just picture this valley going downhill. That glacier is probably hundreds of feet deep. And all that ice, the weight of that ice, is going downhill. And so somewhere under there, it's grinding away at whatever's underneath it. And when it's grinding away, that is abrasion. It's abrading the riverbed that would have been there, the glacier bed, producing a powdery, silt-sized rock flour. That's where we get most of our silts. The sands are the gritty things. The clays are the submicroscopic things. The silt size is basically flour, dust you might think of. That's silt. And this is where we get a lot of silts. And that's why the Midwestern area has a lot of loam, because a lot of that was underneath a glacier and got ground down to a nice silt size, with plenty of sands and some clays and plenty of organic matter. So that's what made such good, rich soils in the Midwest. And then another thing that those glaciers do, okay? I don't know if you've ever noticed this. When there's been, we don't have them much, but when there's been a snowfall, very cold temperatures here, if you're the first person to drive down the road after that, there's usually no problem, is there? Okay? Because the snow is almost gritty, and stuff. You can drive no problem. But after several people have driven over the same track, what happens, you run over the snow, and what actually happens, the pressure makes the snow melt, and then when you release the pressure, it refreezes again. But what was this is now this, so now it's just slick ice. Okay? Well, just think how much pressure is underneath a glacier, okay? So it tends to melt some of the stuff at the bottom, and then, like it gets cold overnight or too cold, and then it freezes, and it may freeze around gravel, rock, boulders. Now they're in there, and they are plucking. That's the glacier water freezes into the surrounding rock and pulls it along, and now it's acting like, okay, if that was a bulldozer, this is the bottom plow, okay? It's just digging up that underneath, and that's called plucking. The rough movement over it, that's abrasion, that's grinding it down. It's like a mortar and pestle, okay? Did Grandma ever take her
meal and flour?
Yeah, exactly, and grind it down and make it into a flour. That's what it's doing at the bottom of the glacier. What the freezing around the boulders and gravel, that's making a plow, and those things are pulling along, and that's plucking, picking them up and carrying them downstream. Okay. Now, here's what happens. This will be a valley glacier. If that fills up with snow, it was water. Now it becomes snow and ice in this V-shaped valley. When glacier moves down it, it grinds out all around there, and that makes a U-shaped valley. It goes from being V-shaped to U-shaped. And that's what you'll see in many of those areas. And this is where you find the waterfall. Where one glacier empties in one that dug deeper, and you'll have a beautiful waterfall there. And sometimes you have steps up and down here. Okay? Those are pretty nice. These behind those are the rock basin lakes where maybe a glacier came and then back and then came again and back, going up the hill, and you get a bunch of these rock basin lakes. When we were near Lake Louise, Canada, we hiked up to this place. They have these places scattered around there that are places where you can stop and rest. And they have teams of people that go up there and man them all summer. I think most of the time they have to helicopter stuff in and out, because hauling them up there is really tough. And we had heard that this place had the best chocolate cake. And we really weren't big into that much hiking, but we thought, for that good a chocolate cake, as much as we've heard, we're going up there. So we made it up. And along with, say again? Well, I'm getting there. Okay, we went up, and there were these little lakes in between. These little rock basin lakes. Just mirror. One was called Mirror Lake. I mean, literally, it was so perfectly flat. The mountains behind just made a perfect picture in it. That was worth stopping and spending some time. But that chocolate cake kept us climbing. So we went on up there. And so I think we hiked probably 3 to 4 miles uphill. That chocolate cake better be good. We got up there and they said, oh no, we have coffee cake. The chocolate cake is the next, and that's 6 more miles. We decided it can't be that good. So we had coffee cake and we came back down. We were really disappointed, but we saw some beautiful, beautiful areas because we went by some of those rock basin lakes on the way. Okay. A few other of the titles here. These were not brand new youthful mountains. They were somewhat youthful, maybe moving in the middle age, but when the glaciers came through, they gouged this down and left peaks again. Oh, is it time? Oh, let's get this one done. And so you had the horns, the cirques. These are the places where the glacier looked like it maybe started and went down. The arêtes are the ridge lines that you have here. They were smooth. Now they're pretty sharp because the glaciers ate out on either side. Rock basin lakes, the steps down here that made little waterfalls. Hanging Valley, that's what that was, which is usually a waterfall. All of the glaciers make the U-shaped valley. So that's most of the features. Don't worry about them, but you'll see these words every now and then. I'm not even know if I'm pronouncing it right. I think this is arêtes or arêtes, I don't know. So anyway, that looks like a reasonable place to stop. Let's see what the next. Yeah, the next slide is going to be wind. I know. So there's a little thing they call mistakes and misunderstanding. There's an old saying, as unchanging as the hills. Well, guess what? The hills are always changing. The change is just so slow we don't notice them, but they're changing. Of course, if you think things are unchanging as the hills, you just haven't lived long enough. Okay, never mind. All right. You've lived long enough not to know that. Okay, let's end this. Oh, no, we'll just go. Okay. You got the lab. Hopefully you've been reading it. Pretty interesting stuff we talked about before. Which are the parallels? These are the things parallel to the equator. They get smaller as you go up, bigger as you go to the equator, smaller as you go down. Those are parallel. You measure latitude by the parallels. Okay? That's what we're talking about here. The ones that are great circles, now the equator is a great circle, but none of the other parallels are because they're decreasing in size. But all of your meridians are great circles because they all pass through both the North Pole and South Pole, so they all cut the Earth exactly in two. And those you measure longitude by, okay? The meridians. The prime meridian is the one that goes through near London, through the Greenwich, England, they call it the Greenwich, and that's 0 degrees east or west. Okay? The equator is 0 degrees north or south. Okay? Now, we don't have the clay. We're not going to do that part of it. Okay? But I do want you to pay attention to the illustration. That's what we would do with the clay if we had it. Okay? We would take the clay, cut it halfway in this way and halfway in that way, cutting out one wedge out of that ball of clay. Okay? If you put a protractor in this way, you're measuring how many degrees north of the equator you are. Since we're in the northern hemisphere, we'll do it that way. If you flipped it over, you'd be measuring how far south. And then the longitude would be how far east or west you are from the prime meridian. This is only showing east if you put prime meridian out this way. That's what your protractor, that's what your procedure would be if we were playing with the clay. And there's the protractor showing latitude lines with 90 degrees straight up. And so lay the protractor flat, you go 0 to 180. That's the longitude. Okay. Now, again, you do need to read.
There's an extra page in here.
There's a okay, not all of them have an extra page. What is it?
The 342 is printed twice.
Okay.
In mine.
Yeah, you have an older one.
I mean, it's no big deal.
Yeah. I gave her. Okay. The older ones have that, so just ignore the extra page. The newer one she printed correctly. Okay. She printed a double stack for me 1 year, and I just now finished using. I guess it's last summer or last spring, and just now I finished. Okay. I think what happened, she couldn't find them, and I went down to get them, so she printed them again, and later found them. She put them in someone else's box. I don't know. So anyway, from your reading, especially that first page, you should be able to answer question 1, question 2. Okay? Now, question 3, you will use good old handy dandy Alabama Atlas and Gauge. Okay?
You still make those?
I guess so. My wife got one years ago, and then she got a newer one, and I brought the old one here to work. So I guess it's still makes it. All right. If you want to find out where you are approximately, both on the inside cover here and on the back cover here, you can find out about where you are. Birmingham's right there. Bessemer is in 30. Birmingham partly in 30 and partly in 31. Homewood's in 31, it looks like. So you can sort of pick out where you are. So you figure out where you live. Because question number 3 says, according to a map, here's the map you'll use, or a globe, don't use the globe, use a map. What is the approximate latitude and longitude of the place where you live? So I'm going to open up to the one we've been using before, which has Bessemer in it. Oh no, this is it. I'm sorry. 31, 30's here, 31's here, so it goes right across the page. So Birmingham's right in the middle. So you find where you live. If it's not on this page, it may be on that page, it may be on this page, or it may be above, below. You find where you live approximately here. Turn to that page number in the text. Find approximately where you live, and then your latitude you read here. And this gives it in degrees, minutes, and seconds. Most of the time you won't know latitude that precisely. But this, because it's a big scale, you can see that. The longitude you read across the bottom, and here again you're given in degrees, minutes, and seconds. Okay? So there are going to be multiple things to do. So when you get your turn, do look it up, find out what the latitude and longitude where you live. Okay? If you can't get to it, yes.
Wait, are the first two questions we have to answer from the reading, or?
Yes. The first 2 points on the first page.
Yeah. Yeah, from your reading, or if you just know it off the top of your head, that's fine too. But it should be, I think, pretty much what you need to know is in the reading here. You may actually have to look in the books on too. I don't know. Okay. Number 4 says explain how minutes and seconds are used to identify a location more precisely. And again, I think that's probably, there is a little paragraph that talks about that too. A sentence or two will do. Okay? Now, number 5, you can wait till the end. Oh man, that's only 5 points worth out of 25. We gotta come up with 20 more points worth. Okay. How are we gonna do that?
We're going to make each portion 25 points.
Yeah, I'm planning. We'll get the
What do you thought we were gonna do?
Whoa.
All right.
We're going to drink Pepsi.
Good, yeah, to go with your chicken. Okay. Now, I have here cups labeled with various continents or areas. I don't know where to put them. I think I'll put them on my desk here. Okay. All right. Here's the Africa Cup. Here's the Alabama Cup. Here's the Asia Cup. Here's the Australia Cup. That was a boat race, by the way. Okay. Here's the Canada Cup. Okay. Here's the Europe Cup. Here's the South American Cup. And this is the United States Cup. Okay. Now you'll find in these cups strips of paper with pretty lousy handwriting on them. I can't imagine who did that. And I just happened to pick from the Asia Cup. It should have been, I'll have to check to make sure, a name of a city. Okay? Now what I want you to do, you need 20 more points worth. So I want you to pull out 10 cities. Now the trouble is, I've only got 8 cups. Okay? So you'll get 1 city out of each cup. Okay, now, you can do it however you want to. If you want to get a separate piece of paper, you can do that. I think you could probably get them all on the back of your page. Got a blank sheet there, right? So write your city down. So once you write your city down, put it back in the cup. So get 1 from each cup. You'll need 2 more. Okay? And I'll let you choose any 2 of the following 3 cups. Africa, Asia, or Europe. Those have the most cities in them. So you pick 2 out of those 3 cups. 1 out of one, 1 out of the other. So you'll have 1 out of each cup and 2 out of 2 of the 3 cups. So you'll have a total of 10 cities. Okay? Maybe 2 from Asia, 2 from Europe, and 1 from each of the others. So 2 from Africa, 2 from Europe, and 1 from each of the others. Yeah, something like that. So you have 10 cities. So write down your 10 cities, okay? And then you use the atlas. Now the Alabama Cup, you will use this atlas, okay? The same one you use for, it won't be the same page probably, the same one you use for your local latitude and longitude. For the U.S. Cup, the 1 city you get out of that, you'll use the U.S. atlas, okay? Now these are a little harder to find the things on. I'll help you find them. Now, once you get out of Alabama, you're not going to get minutes and seconds anymore, or not often. You might get minutes with no seconds. Okay? So that's where you're used for US. Okay? For the other cups, then you'll use the atlases. That's why these are here. This is the Hammond Atlas of the World. Here's the Britannica Atlas. Here's National Geographic Atlas. Okay? I'll put it here.
So let me ask you this question.
Okay. So, you'll draw your names. Be sure you get 10 cities, 1 from each cup, 2 from 2 from 3 of the more populous ones. Europe, Asia, or Africa. 1 each for extra, 1 from those. And then start finding latitude and longitude.
So we opposite, like, what do you general?
Well, say, yeah, you use these to get your latitude and longitude. Okay? And if you have trouble reading a city, ask me. I wrote them, I can figure them out. If you have trouble finding them, I will help you do that as well. And you can work together. This is a lab. Okay? You can work in 2s, 3s, as many as you want to. Okay? So help each other out. So you got a few questions to answer. You have a couple things you can get out of this atlas, 1 thing you can get out of this one, and bunches you can get out of those 3. Work together, share, continue. Okay, I'll bring my paper up, however you want to do it. If you get 1 each, then you got to put them back in the right cups. That's why I would suggest that you write down, put it back in the same cup you got it from. That's Kinshasa, Congo.
Yeah, you got it, right? Don't get that leave.
Yes.
Can you not make this real quick?
What's that?
Okay, so I'm right about here.
Okay. Okay. That's the latitude line here. There's that's your latitude. Oh! Let me be sure to say this. Okay. When you're giving a latitude, okay, you have to, and longitude, you have to include a letter with it. Latitude is either going to be N or S, north or south of the equator. Longitude is going to be either an E or a W, whether you're east of the prime meridian or west of the prime meridian. Okay, so you need to put that, not just a number, but also a letter. In S for latitude, E or W for longitude. So be sure you do that. Okay, now, you remind me of that. So here's the latitude line closest to where you said you were. Where did you say you were? Okay, so take this. Oh, okay. Okay, well then, yeah, let's say those 3 across here, degrees, minutes, and seconds. Degrees. Okay. Yeah, because we're north of the equator. Aren't we? So you were there, so that line there, so you could probably read it right there. Got it? Oh, sorry.
Is this Dolly Indian?
Dolly, it's probably, yeah, Delhi is how you say that. PHLI. By the way, it's capital G, not the largest city, but capital. Okay. So, I'm going to turn off the projector. I don't think we need projectors.
East.
Okay. Oh yeah. Are you asking about east and west? Okay. Picture it. Okay. You can. Yeah. Look at the globes. Okay. Here's the prime meridian through England. Okay. We are which direction from the west.
Said 2 from here.
So if you need the globe to help get your perspective of it, you can use it.
Once you get your longitude method, then I can get this audio.
Yeah. So now you'll also, when you pull out of the cup for Alabama, you'll need it back again. You. Was that? Am I covering somebody's nose? Which one have you got? What have you got? I'll help you.
I know Selma, that's Alabama.
Yeah, that's Alabama.
Is that South?
Say again. Selma, Alabama. Amman, Jordan. Okay, what are you looking for? Yeah. Okay, let me say I didn't read them all. Panama City, Panama, Dallas, Texas, Brisbane, Queensland, Australia. That's in Australia. Brisbane's the city, Queensland's the state, and Australia's the country. And the continent, by the way, too.
Auckland, New Zealand.
Say again?
Auckland, New Zealand.
Auckland. A-U.
Oh, that's a U.
Yeah, that's a U. Ugly writer, whoever did that was really smart.
I remember who did that.
What's that?
I saw one who did that.
I don't know if he was such a jerk. You know?
Sounds so exciting. What? You said Europe. Europe ain't out here. You got Europe to do.
But Europe is one of the cups, yeah.
Really?
Yeah. Probably that one.
You got to have 10.
Yeah, you need 10 cities. One from each cup, and the second city from either the two of the three, Africa, Asia, or Europe. Where is it? Oslo, Norway.
This one was?
Yeah. It's Europe.
What about this one? Bern?
Bern, Switzerland. So for Copenhagen, Denmark. All right. Yes, sir.
It better be 6.5. So, well, I'm looking for a early stage. This was right in the middle.
Here's Fairfield. It's near the. They may not list it. It's part of the city. Oh, you did see it?
Right here.
Yeah.
See there? Right on that line right there.
Mobility.
Okay. Yeah. This is longitude.
He said Africa, Europe, or whatever.
86, 54, 00.
Africa, Europe.
Okay.
I think.
We're in here again, right?
Yeah.
Yeah. So you can go either the upper or lower.
I can do one of them?
Yeah, either.
Okay.
Yeah.
Right here. The 9 is in between.
Yeah, well then you can either extrapolate or see this is 33, 28, 07 and a half.
Yeah.
This is 33, 32, 30. So pick one in between 10 or 15. Yeah. Okay. Either one of them will work.
I need it.
Okay.
Okay.
Yeah. See, that's why we can work in teams.
86 degrees. Monrovia, Liberia.
What's that?
Monrovia, Liberia.
Liberia, that's Africa, right?
8400.
Sorry. Pick another one then. I didn't say that.
So how do you look for the?
Okay.
Should I have all 7 of them in the right?
What's that?
I'm kind of like bumping into everybody.
1, 2, 3, 4, 5, 6, 7. Okay.
Is there?
Okay, this is Africa.
Doll.
This is Algeria. Okay. This is Europe. That's Canada. That's Asia. That's Alabama. That's Africa. So you got your 2 Africas there. That's Australia. There's another Europe. Didn't have a Europe. Yeah, there's 2 Europes. There's South America, and that's U.S. Yeah, you're fine. Perfect. Yeah, what you say?
Yeah, I don't recall this.
Okay. So, here. Okay, now call it. Let's say we're closest to this one. Then across here, there's 33.
33, 19, 22 point.
Right. And it's closest to this one, which looks like you've got here to read.
870.
Yeah. Right on the middle. 87. Pretty
So
close.
just write these down?
Yeah, you're right. Okay, and be sure you put N or S with the latitude, and E or W with the.
Okay. Is this
You know how to get
Canada?
that. Is that what?
Is that
It's
Canada?
Amman, Jordan. AMM.
Is that from Canada though? 'Cause
No.
I
That,
just got that out of the Canada Cup.
Okay, let me put it back. That is.
Like Africa?
No, that would be Asia probably.
Okay, what Tanner, which one do?
These are all mixed up. Russia's in Africa.
I didn't do that.
It's Russia.
Okay.
That's fine.
Okay.
What time does it start?
Russia's not in Asia, is it?
I need Asia Cup. Where's Asia
Right
Cup?
here.
Okay, well there's a
Is that what it comes? Russia's in Asia?
Yes, it is.
Oh,
Yeah. And so is Jordan. Yeah. Yes. Okay, let me just show you this. You see, there's Russia right there. This is in Asia, and Jordan is right down here. That's this is Africa. That's still Asia. Jordan's right down here. Can't find it. Yeah. They call it Asia Minor. Have you heard that?
I mean, yes,
Yeah.
I guess I have, but that's weird.
Yeah, it is. Asia's the biggest front.
Logan's over here.
Yeah. Sam, you wasn't paying attention, were you?
Okay, again, everybody.
Yes, sir.
Okay? For latitudes, you put a number.
That's right.
You also put either N or S for north or south. North or south of what? The equator.
Yeah.
You know whether you're north or south of the equator. On latitude, you put East or west?
EOS.
East or west?
Prime Meridian.
The prime meridian.
Girl.
Okay.
That's right.
I was just 2A.
Yeah. 2A and 2 Europe, and I forgot the other.
Which they're all mixed up. So, I think as long as you have
They made them question 5 on
Yes, east.
So go down to Birmingham, go back to Birmingham. Same as they want to. Get my real on. That long,
All right.
Here, not there. So why would it be 13?
Just pick either one of them. Yeah, it's close to the 13. That's fine.
Okay.
Oh, we can guess the make. Get your,
it was 2 A's and what else? It was either Asia, Europe. I know it was one
the
of them.
number's so small, you can imagine. Two from either Europe or Asia, I believe.
Here's another atlas. There's not being used, but okay.
I was going there. That's my first one.
Mr. Fowler.
Yeah.
If I'm looking for Dallas, Texas, and
Yeah.
I'm here, I see saying that has numbers here.
Okay, right here.
Oh, okay. So it's here, three is going, and that's all is that one, that's going north, right? He said in the neighborhood again.
Okay, it was 2 Asia,
What? 2 Asia, 2 Europe, and 1 from each of the others. That's fine. You could have done 2 Africa, 2 Europe, or 2 Asia, 2 Africa, or something like that. 2 from 2 of them, and 1 from each of the others.
Oh, okay.
You get a lot more precision.
You don't.
Okay, what are you
So
looking
this
for?
will go by city, Grove Hill.
Okay. Oh, you got
Grove is there with.
No, I mean. I'm sorry, we've seen here already. So they say. Oh, yes, yes.
There it is. What have you got so far?
Where's the United States Cup?
That's Perth, West Australia. PERTH. Perth. Okay, you got one from each cup, right? Okay. So from two of the cups, two of the following three cups, pick a second. Africa, Asia, or Europe. Okay, the second one from two of those three cups.
Do you have any more of those?
Okay. Where are our atlases? I see. Is that it? No, that's not. Oh, there it is.
Boy, Bob.
Hey, look. That's when she was in there making them faces. Like she was sitting on the hood, making on the hood.
Yeah.
She's looking at you like, I didn't see that. I got one.
You know you're going to do your hometown, but it's separate. Then you do one from each cup, and you pick a second one from two out of three, Europe, Asia, or Africa.
So you pick two from every cup?
No, pick one from each cup, and pick a second one from either Europe, Asia, or Africa, two of the three cups. And I would write them, say, back of the page or somewhere. Write those first.
I already wrote my hometown. Do I need to write it on the back again?
No, your hometown was in the other. The 10 are from other. That's, you pick one from Alabama.
Yeah.
That's not going to be your hometown, I bet. Okay. Well, I picked them further away.
Just circle, look at it.
What are you trying to find?
I'm just observing
Oh, I
all
see.
the cities that I just wrote down.
Okay.
I'm seeing where exactly they're at.
I see.
Fine.
All right.
Okay, Google. Oh, my bad. I did. My phone was
Just went into Europe because we pulled out Ecuador.
Okay, that would be South America. That happens when too many fingers get in the pot.
Yeah.
That's Canada, yeah.
Ecuador, where does that one go?
Ecuador is South America.
South America.
It's not no I in team.
Oh,
Wow.
Okay.
Yonder, that's a Y. All right. R-I-Y.
It's Riyadh, Riyadh, Saudi Arabia. That should be Asia.
Got Berlin,
May I go?
Germany.
Yeah, sure. If
We're
you're
done?
ready. Yeah.
Awesome. All right.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Huh?
I say, isn't she bad?
The one you get drunk at? It's the one way to make the stick.
What's that? You through?
Yeah.
Good deal.
I'm 21.
Hey, look, hey, when we go,
Where does this one go?
we going down the street to
Winnipeg, Manitoba, Canada.
Who ain't 21?
we just are going right into Brookwood.
Okay, you just spilled cities all over my floor.
No, I didn't.
Oh, shucks.
I should be used to being on my knees because of work, but
Well, I'm sorry, I should be sitting in this chair. I should like.
did I tell you about my plans to go into the military after college?
Oh, really? Yeah.
Going into the Navy.
Navy,
And
fantastic.
going into the officers program.
Excellent. OCS, Officer Candidate School. Yeah.
Straight into the officers program after college because I'm planning to get a 6-year.
Right.
degree.
Okay. Yeah, my nephew did that. I went in the Navy ROTC, so I went while I was in.
Isn't this QUGGNS?
Queensland. It's Brisbane, Queensland, Australia.
Queensland.
Yeah. It was, of course, the Australia was a British protectorate. British,
That's one
originally a
place I
colony.
would love to live. Australia.
Yeah, it's neat. I got to go there twice in the Navy, actually. Amazing. And just I was in 4 years. But actually, one time it was a midshipman cruise before I was in officially. And then my wife got to go there for professional meetings in Brisbane.
Yeah, because I can't find it. The West Australia.
Okay.
What is it?
Perth.
PU.
PER. Yeah, PER. Hey, have another atmosphere.
Sam, y'all need ads? Y'all need ads?
No,
Yeah.
we good.
Are you through?
No, we
Yeah, we're working on it, Bob.
Toronto and Ontario.
What did you ask?
No. Hey.
Toronto? Hey, man.
Canada. Toronto.
Ontario was counting.
Ontario,
Right. he running on one strip.
They're not the same place.
Okay, but you talking to me like I'm the right. I ain't the
Oh, yeah, that's the same place. They're not.
Same state or continent.
So it's not a city in the state.
No, it's two different places.
Look, you know, it's two different places.
Both of them being counted. They ain't the same place.
That's Toronto, Ontario, Canada.
What?
Toronto, Ontario, Canada.
Huh?
The city, the province, and the country.
Oh!
So we're all wrong.
Exactly. So like that's
We all wrong.
Y'all talking about three different places.
I'm like, so y'all sure y'all in college?
Oh, there you go. Oh, yeah. Oh, right. Okay.
No.
Austria. You're in Europe. You're Australia.
Man, I don't feel like going to work.
Is that 40 degrees south?
How did your weekend go?
Australia is one of
She
them.
went up west.
Yeah, I had it.
It was good. Good.
Kiss the thing?
Huh?
Kiss the golf? Well, where the woman from? Or the man?
The man was the talk about it yet on the list.
Yeah, but I thought it was a golf.
Did you say something?
Oh, I don't know.
Yeah, it's a talk.
Oh, someone called.
I did.
Oh, okay.
Yeah, I got my list down.
What's that? 1, 2, 3, 4, 5, 6, 7. 5, 6, 7. You only have 7. What are you missing?
I put all my clips over here when I got done with it.
Okay, you got those two.
No, that's the south.
I got
Yeah,
Australia.
you got Australia. Oh, these are two are in each other. Did you get South America and Africa?
Did I do Africa?
Africa is Mogadishu. Quito is South America. U.S. Oklahoma City. Asia.
I'm kind of sloppy handwriting right there. Does that say?
I'm not sure I see Asia.
No.
Oh, I just picked up Asia.
Jakarta, Indonesia.
Yeah, we all got it on the same.
Okay, you getting a different one?
Yeah.
Oh, okay.
Is that a D right there? Dhaka?
Bangladesh.
Mr. Fowler.
Yes.
There was one that was, Uruguay?
Yeah, it's a good one. Yeah, all of them besides the way. So it's type of way. It's faster than the others.
Canada. Alabama. Australia.
Latitude, longitude for each of those. And there's 4 questions with the question, 5. Oh, you're looking for a city in Uruguay? It's Montevideo.
I found it Montevideo, it was with a V, not a U, and I was putting it in the U.
First question. Yes. Ferrari. Yeah. Probably need to go. This Zimbabwe, that's the country that you gotta find and see.
Zimbabwe.
What's that? Algeria.
Where y'all bad, boy?
What happened?
Yeah, okay.
Yeah. Where is it?
Both of them are
Kinshasa, Congo. Kinshasa. S-H-A.
Oh, Kinshasa.
Kinshasa.
Keep Fasa.
Come to Papa. Okay.
Oh yeah. Can I do it on Kepler's one?
Yeah, sure.
And
Yeah.
it can be an MLA, right?
Yeah, that's perfectly fine.
That was cool once I figured it out.
Yeah, it's not bad.
And I answered all the questions.
Excellent.
We're good to go. And I'll bring
Yep.
my test in next week and I'll take my test on Tuesday.
Okay.
Thank you.
All right.
18 lab due day.
What's that?
18 lab due day.
Yeah, whenever you get it to me.
I still got like 3 more questions.
Okay. Yeah, for the car.
Yes, ma'am.
More chicken.
More chicken.
Yes.
You too, Don. You too.
You're on the East Coast. Algeria is on the West Coast. Okay. All right, if I go on and shut down,
Yeah.
do I have to record anymore?